Diffusion is something that occurs in everyday life without us having to really do anything. The reason for this is that the particles are already in motion unless they're at minus 273 degrees Celsius, also known as absolute zero. So if you've ever made instant coffee, for example, or perhaps put sugar into a cup of tea or a cup of coffee, anyway, you know that gradually it will change color as the step diffuses. So diffusion can happen in liquids. Diffusion can also happen in gases such as air. So, for example, yesterday the home ec class was cooking something really good smelling. And eventually it spreads throughout the entire school and makes the rest of us hungry. It's really hard to show you particles and say this is how diffusion works. So we rely on a lot of animations to help visualize what's going on. So let's say that we were able to zoom in and actually see the particles of the blue stuff that we had yesterday that I added into the solution. So the particles are in water. Do you remember the term concentration? What is concentration?
How much is in there per?
So when we say that there's a high concentration of something, that means that there's lots of stuff in a space. What do you think is going to happen when this divider is lifted up?
It'll mix.
Why?
Because all particles are moving.
And because there's more particles on one side than the other, they will collide together and push each other apart until eventually those particles will be equally distributed throughout the beaker of water. So the formal definition of diffusion is when substances move from an area of high concentration to an area of low concentration. This can happen in both liquids and gases. For example, you see particles going from the left-hand side to the right-hand side because there's more of these particles over here. It is possible for particles to also diffuse across the cell membrane. Yesterday we talked about the stuff that surrounds the cell and acts like a gatekeeper. Now, it only will diffuse across the membrane if it can fit through the membrane. If the particle is too large, it will not go through. It is important to know that the motion of the particles is actually quite random. For example, I can't stop this particle from moving this way, or moving this way, or even moving backwards, because collisions are quite random. However, because there are more particles on the left-hand side here, there will be more collisions, and eventually they will push those green particles to the other side of the solution. We rely on diffusion. It happens all the time without us having to do anything, which is very good. Can you imagine having to tell your lungs to diffuse oxygen every second of your life? Oops, I forgot to tell my lungs to take in oxygen. That's it, I'm a goner. Where does oxygen come from?
The air.
The plants. Okay. Yes. The plants produce oxygen through a reaction called photosynthesis. How much of your atmosphere, approximately?
4%.
This is about 21%. Good job. Which gas makes up the highest concentration?
Hydrogen.
Yes. which is what percent? Hard questions, I say. 78%.
I was getting that.
The rest of the air is made of trace gases like carbon dioxide, argon, neon, etc. And then the class, there could be a high concentration of methane, especially chloride. So oxygen in inhaled air comes down into the lungs, through the trachea, through the bronchi, and eventually goes into the bronchioles until it gets to a blind end sac, which is called the alveoli. The oxygen has to get through the surface of the alveoli into the capillary. It has to cross two cells. It has to cross the lining of the alveoli, and then it has to cross the lining of the capillary. It does that through diffusion. Similarly, carbon dioxide is a waste product that is produced by your cells, and you need to exhale it. The capillaries have the carbon dioxide, and that carbon dioxide has to diffuse through the capillary membrane, through the alveolar membrane, into the lungs, and it is exhaled. The site of gas exchange is this blind end sac called the alveoli. These are representing the cells here and here. When you breathe in air, it's about 21% oxygen, and there is a higher concentration of oxygen inside the alveolus compared to outside the capillary. The blood is traveling from the right side of the heart to the lungs, and around each one of these sacs is one capillary that completely surrounds the alveolus. Notice that you have a color change in these red blood cells. That's actually because of the hemoglobin molecule. When hemoglobin is oxygenated with 4 oxygen molecules, it turns a bright red color. As oxygen is pulled off, that hemoglobin molecule is expected to turn a purple color. It's a little bit misleading to say that you have blue blood, though. It's more of a dark purple when it's deoxygenated than it's blue. The oxygen is able to get from inside the alveolus to the capillary by diffusion, because you have a high concentration of oxygen. Anytime we put a chemical symbol in square brackets, we say concentration. The blood coming to the lungs is deoxygenated, so we would say that there is a low oxygen concentration inside the capillary. So by random collisions and movement, that oxygen moves through both cells into the capillary. Oxygen then attaches to the hemoglobin molecule. Conversely, this blood is higher in carbon dioxide than inside of the lungs. So as oxygen is diffusing out of the alveoli, carbon dioxide is diffusing into the alveoli. It's going from a high concentration of CO2 in the capillary to a low concentration inside the alveolus. This happens without your brain having to coordinate anything. It simply occurs by diffusion. Questions about this? of any other examples of diffusion in the body? Did anybody eat breakfast? How do you get the stuff from the shake into your body? So your stomach digests it, your small intestine digests it, but eventually it actually has to physically move inside the body. So in your stomach and in your small intestine, you have enzymes, which are breaking down all the things that are in that shake. Okay. So what did you put in there?
Protein, water, and blueberries.
Okay. So if the stomach and the small intestine is breaking down protein, what is it breaking the protein down into?
Probably like atoms or something.
Not that small.
Amino acid chains.
Amino acids. Okay. And it looks like there's some berries in there.
Blueberries.
So berries have sucrose, which is a disaccharide.
We got 8
Fatty acid.
What is sucrose broken down into?
Isn't it like glucose and fructose?
Glucose and fructose.
Give me 100.
If you have fatty acids, so have you added yogurt to that or anything? No?
Just blueberries, water, and
Do
protein.
you know if there's naturally any fatty acids in there from hemp seeds or chia seeds or anything like that? Okay. Some of them have that so that you get your omega fatty acids. Omegas are what we call essential fatty acids. Our body cannot manufacture them, so we must consume them generally from plant sources. So those fatty acids will also be broken down into small pieces. Your body then needs to absorb these small pieces, and it does that in the small intestine, particularly the latter part of the small intestine. So this is a cross-section of the small intestine, and what we see here is a bunch of finger-like projections, and this increases the surface area for absorption. This is called a villi. And inside each villi is a capillary network. So we have this blood vessel, which is going to be some kind of arteriole. We have the capillary coming in here. It's also supplying the villi with oxygenated blood. And what will happen is all of those particles that were broken down here, okay, all of those will move across the membrane into the capillary, and then that blood supply goes to the liver. Why would we want all the blood from the digestive system to go to the liver before it goes to the rest of the body?
So it can filter out anything else.
Detoxification. Okay. There's some things we don't really want in the body. For example, alcohol. Alcohol is actually a poison. The reason why it affects your central nervous system, your brain, so fast is because it can be actually absorbed by the stomach. And it gets into your circulatory system quite easily. Normally, what should happen is everything should go to the liver first before it's distributed so that it can break down that stuff. Interestingly, there is a different ability in different races to process alcohol. So my cousins, actually 2 of them are First Nations, both went First Nations. And First Nations people can have a lower amount of what's called alcohol dehydrogenase, which processes the alcohol. And so what happens is if he and I drink the same amount of alcohol for dinner, it affects him more than it affects me, because my body has a better ability to break down that alcohol than he does, which makes First Nations people much more susceptible to alcoholism. which unfortunately one of my cousins does. That's just biology.
That's why
Alcoholism is because you are genetically.
We also rely on diffusion for nerve impulses. I know that you haven't studied nerves too much. This is one nerve, and this is another nerve that's farther down the line. And what has to happen is one nerve has to send the message to another nerve. For example, do you know where your sciatic nerve is? It runs from the base of your back all the way down to your heel. So that means that there has to be another nerve that connects the spinal cord in the brain to that sciatic nerve, so that the brain can say, all right, lift your leg. Otherwise, we wouldn't be able to walk. So what happens is when the nerve impulse gets down to the cleft of one nerve, it actually releases a chemical which stimulates nerve transmission on the next nerve. We can actually block this from happening. So if you can take medicine and block this with the medicine.
Does morphine do that?
Morphine works a little bit differently, but you're on something. This is how something killers work. They actually block your transmission, so your nerves cannot send the sensation of pain to your brain.
Is it like kind of getting shocked with an open wire? Like if the wire's covered by something, then you're not getting it.
Absolutely, that's a really good analogy, actually. Not all painkillers work this way. So another brain killer might work on the brain and tell the brain that what it's sensing is not actually pain.
How do you think people that are paralyzed? How do we train them?
Okay, here's an analogy of a wire. That wire is cut.
But how do they how do you get a person back into?
Whatchamacallit, it's a bone marrow transplant thing.
Nerves do not have a brain.
Stem cell therapy.
Cells. Do you remember talking about mitosis?
Nope.
Most cells really create new cells. Nerve cells don't. So if you damage them, they have very, very limited ability to heal themselves. I think that's going to change your mind. There is a lot of research going into spinal cord, brain development, helping people who've been in car accidents and really bad traumatic brain damage, and helping that to heal. The only thing is, let's say this is the part of my brain that's been damaged by injury, which is the part that is personality to memories. I don't know how to be able to get the pre-injury hunter or Miss Patterson back if we feel to young nurse. You might have to develop those aspects. Some people have, it really depends on how bad the damage is or how bad the damage to the spinal cord is. Sometimes you have inflammation or swelling, so that puts pressure on the brain or the spinal cord, so you're temporarily paralyzed, or you're temporarily some loss of something. And when that swelling subsides, you just kind of irritate yourself. So, a different cousin in Manitoba, actually, he and his girlfriend got sticking drunk. Girlfriend decides she's going to drink because she's less drunk.
That's funny.
This is a really decision. They get into a fight in the car. He decides he's going to get the heck out of there while the car is moving at 100 kilometers an hour.
Smart choice, but
This is all. Literally. He opens the door and exits the car and gets wrecked. Never regained
consciousness.
to walk or function independently. He had to learn how to
That sounds like some graphic
how to
novel.
sleep. Everything. All is important. Oh, you know what? It's probably down here again, isn't it? Fine there. You're fine there. Some drugs can also block these receptors here and change how nerves or brains function. I just want to caution you in terms of not saying that this is how all painkillers or how all drugs affect.
Is that how Tylenol works?
Pardon?
Is that how Tylenol works?
Tylenol is an anti-inflammatory. So what it does is it blocks the immune system response of swelling and tries to reduce the swelling. So if you have a headache, for example, that's right back here. It's going to reduce the inflammation, which is going to reduce the pain. I'm not sure who hit his hand went up first.
Does that mean that ibuprofen or Motrin works the same way as Tylenol?
Yes, they're both anti-inflammatories, but they have different chemicals that cause a similar response. So some people, Tylenol works better for you than ibuprofen.
Ibuprofen works 100 times
For
better.
me, it's Aleve, which is the opposite.
Probably works because I've never used it, but because I noticed Tylenol used to work for me, but I've used it so much in the past that I probably got used to it.
Absolutely no tolerance to those hard. So you might have to switch around.
Yeah.
I used to take Cedrin, which is ibuprofen with a little bit of caffeine in it, and that can help some migraine sufferers. But I only lasted a year and a half on that, but I can't take it at all anymore.
With the nerve impulses, if we use painkillers or something to retract, to retract basically the pain, would we be able to find a way to attract, put anything in those nerve endings that have been damaged in something and attract them to regrow?
Like reverse engineer.
Basically reversing what painkillers is stopping.
I know that you can introduce something to clear that area and restart the nerve impulses. I don't know about reversing painkillers. I think it's a matter of allowing the stuff to break down. When you get frozen from the dentist, for example, it breaks down naturally.
Well, and I think that a problem with, if you were to get into an accident and you were to get, paralyzed or something, I think the only thing that will work and in our time will work is just the physical therapy that you do. Because I think that if you, like Brain said with the Tylenol. With Tylenol, you get used to the medication after a while. I think because if you were to find a development to help your nerves regrow so that you'll be able to walk again or something, I think the heavy doses of medicine that you're gonna get after a while to help regrow is gonna you get used to and not work.
I wish that when it came to working with you, there was a better team approach to that. Because you're right, physical therapy needs to be connected. If you just rely on the painkillers, eventually you have to get yourself off of them, and you have to rehabilitate your body. So, one of the challenges that I've had over the last 4 or 5 months with my rheumatoid arthritis is I've been so inflamed for so long, and now that the inflammation is decreasing, I've lost strength.
Well, and the natural buildup of physical therapy is better than you getting built up off of because in the future something as serious as learning how to walk and talk again. As soon as you're off the meds, that could all just go away because no.
You should retain your memories.
You should retain memory from the medicine.
There is a medication that you can receive that will block the formation of memories, and they will sometimes give that to somebody during a very, very traumatic accident, so that they don't remember being in that accident.
Really?
You can cause somebody to have amnesia.
Nice. I want that.
Why you want to forget to
It's not used very often because you can't really control how much of it you can forget. But it is possible to do that. Here is another really important example of diffusion. Think about it. If somebody is pregnant and carrying a child, how does baby get all those nutrients? The umbilical cord, okay? Okay, but you've got a barrier called the placenta. And stuff has to get through the placenta into the child. And then once it gets into the child, it has to be able to leave the bloodstream and go into the cells. It's not diffusion. Similarly, waste has to go back to the mom, and the mom's body processes the majority of the fetal waste products. This is why some women have urinary or kidney issues when they're pregnant, because you're not just processing the waste of one person, you're actually processing the waste of at least 2 people, depending on how many kids she's carrying. So it's all by diffusion. And thankfully, we don't have to think about this. So here is a cross-section of where the umbilical cord is mom. This is the uterus, and during pregnancy, placenta forms, which is a thickened region right here. Okay, and it's highly vascularized, which means it has lots and lots of blood vessels. You will have mom's circulatory system, and you will have what belongs to baby. Okay. Now, in order for stuff to go from mom to baby, it diffuses through at least 3 membranes. And if we have waste products, that needs to go back to mom. When the child is born, this comes off and comes out. Sometimes referred to as the afterbirth. Alright, before we go on to this, we're going to do some more for the diffusion. How many different types of molecules are there?
2.
2. So we have circles and we have triangles. The next question, you had to count. How many triangles are there on the left-hand side?
12. I got 14.
12.
14. And circles on the left side?
On the left,
12.
just the left side?
And then on the right side, how many are there? How many circles are there?
0.
There's 13 circles. There's no triangles on the right-hand side. Which shape is larger? Triangles. Based on the arrows here showing you potential movement, what direction are these moving?
Random.
They're random movement. They don't have going to one side preferred. Are all of these molecules going to be able to pass through the holes in that membrane? No. The circles will be able to because they are small enough. The triangles will not be able to. This is what we refer to as a semi-permeable membrane. If you left the system for an extended period of time and then viewed it again, would you expect to find any changes in the number of molecules on either side of the membrane?
There could be more circles on the right-hand side
Okay, why?
because the surface in between is permeable by the circles,
Okay.
so they're likely to move back and forth.
Interesting.
So that's likely to move over to the right side because there's more like molecules on the left, so there'd be more collisions.
Okay.
Until the amount is equal.
Interesting idea. Any others? So there's actually not going to be a whole lot of change because there's 12 circles on the left and 13 circles on the right. What's really interesting about particles is they move independently of different types of particles. Although those different particles will influence how fast they diffuse, we're not going to see much change in this because the triangles cannot move through the membrane. And you have 12 circles on the left, 13 circles on the right, so that's already a pretty equal number. If you had substantially more circles on the left-hand side or the right-hand side, you would definitely see more change. The next model does one more important change. Instead of just showing the semi-permeable membrane as a dashed line, it's now shown more stuff inside of that membrane. We have the phospholipids right here. These are the heads and tails structures that we talked about the last time. We have transport proteins which go through the membrane. They are the special gates that allow some things like sugar to pass through. We can also have some proteins on the surface. These could be for something like a hormone. So for example, some hormones don't actually come into the cell. They bind to a surface protein, and that surface protein can cause a change in the membrane or cause something else to happen inside the cell. You have glycoproteins, which will help different things to come in and out. Glycolipids. The difference between a protein and a lipid is what it's attracted to. Have you ever heard of life dissolves life? So, for example, oil and water don't dissolve each other very well because they're not both polar molecules. So, the majority of the particles are phospholipids. Here, and here. And the other main type of particle is the proteins that are on the surface of the membrane or go through the membrane itself. There's 4 different proteins. There is the surface protein, which is unshaded here. You have a shaded protein over here. And then you have this type of spanning protein and the shaded type of protein. This is just to show you that the different proteins will allow different things to happen. Maybe this protein is the one that allows the glucose to pass through, but this protein is the one that allows sodium potassium ions to be pumped in and out of the cell. Surface proteins are found on either side of the membrane, so either on the surface of the inside or the surface of the outside, versus these transport proteins go actually right through. It's like a tunnel going through a mountainside. It allows vehicles to go through the mountain rather than around the mountain. The names of the proteins can help you identify what kind of chain is attached to it. So carbohydrate, you'll often see the word glyco to indicate that the carbohydrate is a part of that molecule, versus a lipid indicates that it is a fatty acid or a lipid chain that's attached to that. The types of molecules that can be moved across the membrane include polar and nonpolar molecules. It does depend on the size in terms of whether or not they can go straight through the membrane or if they need help through the transport proteins. The small polar and nonpolar molecules can actually go right through the heads. So you'll see that there's a little bit of space in between here and a little bit of space in between here. And the smaller points can actually go right through that. Even though there is a barrier in the way, those smaller dots will still go from a high concentration to a low concentration and follow the principles of diffusion. Are there more of those small particles inside or outside of the cell? I'm talking about these small dots here.
There's more on the outside.
Far more. So the direction of diffusion will be from the outside of the cell to the inside of the cell. Can we stop particles from going out? Because if they can come in, they can probably go out. So there will be particles, just by random motion, that are able to pass in between the heads and move out of the cell. But more particles are going to be coming in rather than leaving. It's like the school at 9 o'clock in the morning. Are there people leaving the school at 9 o'clock in the morning?
No, but I bet they wish they would.
Sure. Maybe parents have dropped off their younger children to elementary and then they're going to go to work. So they're physically leaving the building. Maybe there's a field trip that's scheduled to leave around that time, so we have a busload of students leaving. However, more people are coming into school around that time than are leaving the school.
So it's such a called that we usually physics.
Because particles move randomly, molecules tend to move across the membrane in both directions. Does the model indicate that molecules are moving in and out at equal amounts? Look at the size of the arrows. We have an arrow here, 1 arrow, 2 arrow, 3 arrow, showing the particles coming into the cell. But we only have one arrow right here, showing that the particles are coming out of the cell. So there's far more particles moving in than are moving out, so there is not equal movement.
I used to understand.
I did it.